Look at a question, house robber 4, which is the sequel to previous 1, 2, 3. And given an array and k, is you have to steal at least k house, and you cannot steal adjacent homes. And you have to return the minimum capability of robber in order to at least steal at least k house. What's a capability? It means if you can only steal the house that greater than this capability. So for example, you can greater or equal to this capability. So it means you can only steal 2 and 5, and you cannot steal adjacent one. So you cannot steal 2 and 3, and you can only steal 2 and 5. You cannot steal the adjacent one. So given these questions, how can we solve it? And before looking at the solutions, we can take a look about this data structure called maximum presum of a subarray DP. If an subarray ends with index I of the original array, what's the maximum presum of the subarray? It will be. So we define an array called DP, dynamic programming, and we'll take a look in here. DPI is 3, and DP0 is 3, and DP1 is, if you only stay with here, you don't want to include this one, you are -5. But if you want to expand to the left, you have to +3, which is -2. And index 2, if you want to stay yourself, is 4. However, you want to expand to the left, you have to -2, plus -2. Then you choose stay yourself only. And if you want for index 3, if you stay yourself, -2. If you expand to the left, +4 is 2. Then you choose the later one. For index 4, the DP index 4 is you stay yourself is 3, but if you expand to the left, then you plus the expand to the left. And if you is 5, then you choose 5. For index 5, if you stay yourself, is -9, and if you expand to the left, +5, which is better, then you choose -4. For the last one, index 6, if you stay yourself, is 4, but if you expand to the left, +-4 is 0, then you choose to stay yourself. That's how we construct this DP array. How can we use that? And if we add one condition, which is you cannot choose adjacent pair, how can we do that? So for DP0 is array 0, but for DP1, because you cannot choose adjacent pair, then you get the maximum of array. So how about if you add another condition, which is you cannot choose a adjacent pair? Then in this case, DP0 is array 0, and DP1 is the maximum between array 0 and array 1. And how about more general case for DPI? And if you can put it into two conditions. One is you want this array I, another is you don't want and you want. And if you don't want, it's equal to DPI -1, because that's the best for you. And you cannot do DPI -2 because it have to be consecutive. And for array 1, and for DPI is if you only want array I, then it's array I. But if you want to add more, if this is better, if DPI is positive, then you can add DPI -2. So in this case, let's take a look about the pseudocode of our algorithm. So you're given an array, then this n is the array size. Array n equal to 1, you return array 0. If n equal to 2, you return the maximum between array 0 and array 1. And for DP, then we initialize the DP array with size n, and DPn equal to DP0 equal to array 0, and DP1 equal to the maximum between array 0, 0 and array 1. This is the corner case. And we start from array 2. You have three possibilities. Then one is you don't include array I. Then the best case is DPI -1. And if you choose array I, then you can choose either itself, or you plus dpi minus 2. There are 3 possibilities. We get the maximum of this 3 possibility. Then you get dpi. Lastly, you return the last element of this dp array, which is the maximum presum that have the do not choose the adjacent pair, have the condition of do not choose the adjacent pair. You get the maximum presum of this original array. Now let's go back to our original questions. So you can say the original questions as at least still k room, and you cannot choose adjacent pair. In this case, we can see we can use a binary search to do it. How? You can put the left pointer to the 1 because the minimum is 1 and the r represents the maximum of this number. So it doesn't represent the individual value of this original array, but the smallest and the maximum of this array. So you get a range from it. You can see if you just search from it, if it can have the condition, if you get the middle point, you try to check the condition that whether this middle point can rob or not, satisfy the condition that at least k horse this requirement, whether you can satisfy this requirement. If yes, you can say, then you record down this answer. If it's as a potential result, record this answer as a potential result. It's satisfied, then you record down this answer as a potential result. It's a legible cap, but maybe it's not the minimum answer. But if it's not, then you try to move the left pointer to the middle point and keep search. This one is minimum to maximum. It's nothing related to the real value, the really individual value of the original array. It just arranged from the minimum to the maximum. You get the middle point, then you if it's greater, then you the r go to here, then you go to the left part, which is this one. And if it's not satisfied, it's not eligible, then you go to this part, right? You go to this part, your L pointer move to the middle point, then you go to this part to search. Okay, then you return the answer. That's the whole condition. The rob is the pseudocode we wrote just now. So, and with only one condition, that whether it's greater to k or not. So we can take a look about this rob function. So you can see this rob function is very similar to our previous pseudocode. Given array and your ability x, if array is smaller than greater than x, then you can steal this index 0, which you can't 1. If it's greater than your ability, you cannot steal is 0. Same logic apply here. If it's both array, the opposite condition is both greater than your ability, then you cannot steal. It's only 0. But it's one of them satisfied, then it's 1. Then you go to initialize a dp array of size n. It's the same. dp 0 is array 0 only if your ability is greater or equal to the array 0. You can't. And it's the same condition as here. And from array index i equal to 2, you have 3 possibilities, and you will get the maximum of this 3 possibility. Lastly, you return the end of this dpi, which is the maximum sum. Okay, so can we optimize this algorithm? Yes, we can, because in here you can see you only utilize the very adjacent previous one. Then you can see you only utilize the previous adjacent one. Then you can create a condition called last, represents the array 0, last equal to maximum between array 0 and 1. And you change the dp array using 3 variables to replace them. In our code, you can see it's very similar to the left side. This is the optimized code. This is dp0, dp1, and dp1 is still last, and p2 is 0, but it's actually a combined condition for p2 and p3. It's a combined condition for p2 and p3. Only if the only if the number I is smaller than and equal to your ability, then you start to assign the p2 to a proper value. The reason is, if array I is greater than the x, if the opposite condition, if the else condition, then p1 is definitely larger than p2 or p3. The reason is p2 is 0 in this case, p2 is 0, and p3 is 0 plus dpn minus 2, and dpn minus 2 is definitely smaller or equal to dpn minus 1. That's the reason. Then you get this optimized code. This code, you can see, don't use the dp array. It only use 3 variables, which is last, and current, right? So you can get our final code for this house robbery question. So last, and current, and it's a whole code. It's a final code for our question.